everyone, good morning. Today's TIE Talk speaker is Kevin Wu, so please give him a warm welcome.
Thank you, everyone. Thanks, Carson. So, like you said, my name is Kevin, and I'm here. I'm excited to talk about my job. I'm a senior digital electrical engineer at NVIDIA, and I understand that you had a TIE guest speaker before from NVIDIA as well, and I believe he talked about AI and the different aspects of AI. And here, I'm specifically here to talk about electrical engineering aspect at NVIDIA. So I think it'll give you a different perspective. Same company, same goal of AI, and get exposed to engineering side of it as well. So before I get started, I wanted to start with the end product of what I work on. So here, this board here is, if you stack about 100 of these, that's what you get called a data center. And data center is what powers something like ChatGPT and AI. And in the middle of these boards are these silicon chips. On the left side, this is a GPU, it's a graphics processing unit. And on the right side, it's a CPU, central processing unit. And so as a digital electrical engineer, this is what I specifically work on, the chips. So design and verifying and things like that. So just wanted to take a step back and then start with how did I end up as a digital electrical engineer. So kind of my journey is that I went to UC San Diego and I majored in electrical engineering. And electrical engineering is a very, very broad major. You can go into many different fields and areas. You can do digital engineering, you can do analog engineering, you can do signal processing and different things like that. So when I was in college, I didn't really know what I wanted to do with electrical engineering yet. So then you have to take classes in each of the areas to know, okay, what do you like? What do you want to get into? So I took a class in digital engineering, and I really didn't like it. I took a quiz, and I got a 0 on a quiz. And I studied for the quiz. I was at the quiz. It's not like I missed the quiz. I was there, but I got a 0 out of 10. The professor kind of intended it because the class average for that quiz was 1 out of 10. So he kind of intended it to be that way, made it really hard. But I was a little bit traumatized. I was like, a 0? I never got a 0 before. If I sleep through the quiz, sure, I get a 0. But okay, I got a 0. So then after that, I didn't do anything digital engineering related. I said, I don't want to do this anymore. So then I geared all the classes and even my master's degree, nothing in digital engineering. So I graduated from UC San Diego, and then out of San Diego, I worked at Northrop Grumman. It's a defense company, and I worked as an integration and test engineer. And so I was still, just a couple years out of college. I wasn't really sure what I wanted to do, and then I wasn't sure which direction I should take my career. And then while I was working as a test engineer, there was a couple months in the period where I won't have anything to work on. It's very projects-based. So then they're saying, okay, well, we don't have any projects at this moment. So I had about 3 to 4 months where I won't really be able to work on anything. So during that time, I sent emails to all the managers that were at Northrop in my sites in San Diego. I sent an email to software manager. I sent an email to digital manager. I sent an email to all the managers saying, hi, my name is Kevin. I work as a test engineer at Northrop. I have, 3 to 4 months. I'm a new grad. I don't have too much experience, but if you're willing, I can work. I would love to work in that department. The one department that reached back was digital engineering, and I was like, oh no, that's the one field that I didn't really want to go into. But yeah, the manager answered, and so I told him, hey, I only took one class. I didn't really like it. I don't have any experience in digital engineering, but he was willing. So then, from then on, I switched to digital engineering within Northrop, and I had to learn everything from scratch at the job, once I switched. So I learned everything, and then I worked a couple different jobs and locations I didn't put on the slide here, but eventually I'm working at NVIDIA right now as a senior digital engineer. So then I wanted to give a very brief, very basic overview of what is digital engineering. In digital world, you have basically 2 alphabets. It's just 0 or 1. And so to communicate, let's say hello to someone using only zeros and ones, this translates to this 0, 1, 1, 0, 1, like combinations of zeros and ones to communicate just this 5-letter word, hello. Computer only understands zeros or ones. So wanted to talk about then, so that was a very high overview, but talk about the real life different examples of then, so we're designing this chip, right? And then you get a bunch of zeros and ones coming in, and then a bunch of zeros and ones going out. So then what's the purpose of it? Like, what's the application of it, right? What is this chip used for? So I thought of a couple different examples that I've worked on throughout my career. So first example at Northrop, what I was working at was a radio. And you might be like, well, who listens to radios anymore? We still use a lot of radios for, like, let's say planes, communicating between planes. And actually on your phones, if you have 5G, that's a form of a radio. Okay, so then the input here, what you see is, this might be the input. And this is what is called frequency modulated signal. So that's why on your radio, you have a FM, frequency modulator, or AM, amplitude modulation. So when it's slow frequency, like in the beginning here, that signifies the signal 0. When it's fast frequency, that means it's a 1. And then when it goes back to slow frequency, that's a 0. So this is the input, let's say, to my chip, this frequency modulated signal. And then I'm demodulating that signal. And at the output of the chip, I might have a 0. Start with a 0, go up to a 1, and go back down to a 0. So an application like that might be for a radio. I also worked at a medical company. And this application was cool because I was working, so the input of it is an ECG signal. It was a watch, right? And then you get an ECG signal coming in. And let's say the patient is wearing a pacemaker. A pacemaker is when it helps the patient initiate an electrical response to your heart, to help beat your heart, right? Well, let's say the patient is wearing the watch and we're receiving an ECG signal. We have to know whether this is a real ECG signal or if it's a pacemaker ECG signal. Because let's say the patient is no longer, their heart is no longer beating. Well, we don't want to accidentally report the pacemaker as like, oh, this patient is still alive and beating. So we have to then filter that signal out. We have to identify, oh, this is a pacemaker signal, which it looks a little different from a regular human heart ECG signal. And then we'll have to output if it's a pacemaker signal, we'll filter it out. We won't output anything. We only send out the ECG signal. And right now in NVIDIA, what I'm working on is, at the input of it is a camera sensor. So like we have cameras here. Inside the camera has a little sensor that is exposed the images and converts it to zeros and ones. Every picture, every frame gets converted to zeros and ones. So in the chip, I'm converting that and packetizing it into an Ethernet packet, so that you can connect just your, you've seen like those Ethernet plugs. You plug it in, and then you can plug into the NVIDIA system processors so that you can do AI software on those images as well. So those are a couple different like life examples of what a chip does, right? It can do. And those are just 3 examples out of many, many different applications that we can have on a chip as well, right? So then, what does my day as a digital engineer look like? So most of the times I'm writing Verilog code. So if I'm working, and if you were to just kind of walk by and look at my screen, you might assume I'm a software engineer. But if you talk to a software engineer, they'll be like, oh, he's not a software engineer. I mean, he's not software, but I'm more of a hardware engineer. So I write the code, and then I simulate the code. So this is called a wave diagram. So I look at this like most of my day. I write it, simulate it, look at it. Does it look right? So on the top here, you see that it's it goes from a 0 to a 1, 0 to a 1. This is the clock, and then on the edges of the clock, we have these logics that are coming in. So you see zeros and ones. Basically, I sit there and go 0, 1, 1, 0. Like, does it look right? Does it look like what I designed it to be? And also, on the other side of my day, I have a lot of different meetings with different people. So I might work with my managers, the project leads. So we need to define the requirement. Like, what is the chip going to do? Like, what is it going to function? I have meetings with other design engineers. We split the work between us. We collaborate together. We have separate verification engineers. So I design, and then the verification engineers will thoroughly test my code. They'll come back and say, hey, there's a bug. Is this a bug or not? And then we have meetings. And then we also meet with the software engineers. So this chip, the example that I gave, goes out on Ethernet. And the software engineers, they have to then process the image. And so I have to work closely with them. So actually end up having a lot of different meetings with a lot of different people in different areas of job function as well. So a lot of collaboration, a lot of interactions as well. So then we'll be talking about the Tide connection, like how is my job connected to the Tide values. First, technology. So digital design is constantly evolving. They say the Moore's law is every 2 years the number of transistors that fits in the chip doubles. And so back when I started in Northrop Grumman, I think we were probably talking about for Ethernet, maybe 1 gigabit or 10 gigabit kind of Ethernet speed. Right now, it's been maybe, 7, 8 years. Right now we're talking about 400 gig and 800 gigs of Ethernet. So in the span of a couple of years, we're constantly evolving the rate and the speed of technology. So, and we also want to design smaller and faster chips. So every generation we want to have, the next chip that's better and more power efficient and things like that, right? Innovation, so what can we do to improve our customer experience? So my customer might be that software engineer who's at the receiving end. Or, in our meetings, we talk about the users of these data centers, right? How can we improve their experience so that they'll want to come back, they'll want to buy the next generation. It's more power efficient. Right now there's a lot of talk about, because each of those GPUs consume a lot of power, 600 to 800 watts. So we want to, and you pack hundreds of those. It's going to be a lot of. I once walked into a data center rack, and it was really loud. It was like I was in an airplane because there was fans that were on to cool the system down. Some of these data centers that are located below, in the sea, because it's naturally cold around them. So it naturally just cools the data centers down. So a lot of different aspects to think about when designing the chip. So for design, it all kind of ties together, right? The logic that I kind of showed you, the wave diagram, there's many ways I can code that thing, right, to work the same. But there are different ways to code that's more. One might be more area efficient, make the design smaller to fit into a smaller chip, but it might be less power efficient, or it might be more power efficient at the sacrifice of an area. So these are kind of the different things we have to consider when designing as well. And the entrepreneurship, I myself as an engineer is not too involved in the entrepreneurship aspects of things. But for my job, if I want more jobs, if I have more customers, yeah, that's great. And so in summary, a couple of different things I want to leave you guys with is don't let one bad experience deter you. I told you guys about my quiz and got a 0. I never wanted to do digital engineering ever again. I really didn't think I would be a digital design engineer right now. So explore for new opportunities. So how I ended up in digital engineering was that I emailed different managers to ask for opportunities, and then that's how I kind of went in. While I was in college, I did a similar thing. I was looking for a research opportunity, emailed a bunch of professors, and then, hey, similar, I don't have much experience, but would you be willing to take me on? One professor responded, so I got to do research with him for a couple of years. So explore for, as you look for new opportunities, I think you'll be exposed to different things so that you can know if you like it or not as well on top of it. And lastly, there's always a learning curve to anything. As in, when I first entered into digital engineering, it was hard. Part of why I didn't like it was that it was hard. There was a learning curve, right? But there's always, to any new skills, there's always a learning curve. So it's always hard at first. You're not used to it, but don't give up. And so once you start getting used to it, once you have more skills, once you start growing in your skills, you'll also grow in your confidence as well.
All right, we'll open it up for questions.
So I know you talked about how you kind of the AI applications and working on the board designs. I was wondering, like, what kind of programs have you worked on? Because I know that NVIDIA has thousands probably of individual programs for that stuff.
Okay, so the question was like AI applications specifically, right? So for my job specifically, I don't work on, so that's like the software side. I'm right before software. So then those applications, how you actually program the AI, that would be for software engineers. And then I'm kind of providing them the data that they need to be able to do software, the AI. So I'm at a level before them. So software is my customers. I help them. And then software engineers, they are the ones who will actually do the AI itself. So an example of, so I talked about the camera and the Ethernet. An example of the AI that's involved in that is for surgical, like robotics. So then when you do surgeries, they have cameras, and then they'll, your hands are in there, like in the camera. Let's say you're looking at a body and your hands are in there, then it'll like blur your hands out so that you have a full view of the body. Or when you have to kind of move, let's say you have to move around, the camera will automatically follow you, so that because right now those surgical doctors, they have to move. If they have to move, they have to reset the camera and then go back and work. If they move again, they have to reset the camera. So those are some of the applications, at least in the medical field, that we have for AI. So yeah.
What are some major projects that you are?
Major projects. So main one is that camera sensor to Ethernet. The other one is in that picture that I showed you with the GPU and the CPU. So on that board, there's another chip that communicates between like the computer and to the GPU. Like we need to get, what's the temperature of the GPU? Is it overheating? Do we need to shut it down? So I need to communicate. That's another like application is, the example that I gave, like hello, like we need to communicate between GPUs and software computer. That's what those are some of the projects that I'm working on right now. Yeah, so, yeah.
And what does the outlook look like for just the specifics of being a digital engineer in the future? Like let's say 10 years from now.
An outlook. So for digital engineer, there's always a need for silicon chips. In your phones, there's silicon chips in there, and then like there's always they're always trying to make the chips smaller and more power efficient. So if you've heard of maybe an Apple like M1 chip, they might be like our new 5 nanometer chip, right? And it's more power efficient. It's kind of the different things that I've talked about. So maybe a year from now, I'm gonna have to talk about so NVIDIA already does like 1.6 terabytes like of communication in between the chips. Later on I might be like petaflops, which is like thousands of terabytes. We just keep on increasing in number of data that's transmitted. So there's always a need for designing silicon chips as well. So if not,
why is it very important to work on the silicon chip and having them as small as possible? Wouldn't you be able to have more benefit if you'd have it access to more power by having it larger? But why is making it smaller an important aspect?
So let's say for your phones, right? Like the chip needs to fit into your phone. So I brought a chip here, one of the chips that I used to work on. So let's say this is one chip that you've worked on, and this is a phone, right? And it's not like it's just one chip that's on the phone. There's many other kinds of chips as well. So if I had, let's say, I can't fit about 16 of these chips on here. So then I want to make this chip smaller so I can fit more functionality onto the phone. In the picture that I showed you, that chip is huge. Like the M1 chip on your MacBooks, they're huge. So for data center applications, we're not as constrained for area. But when you stack hundreds of those, the picture that I showed you, it's literally like racks and racks it'll fill up this whole room of the data center. So if you can make that a little bit smaller, then maybe make it into a something like a tablet, then we need to keep making things smaller as well.
Okay. Thank you everyone so much for listening to today's TIE Talk. Please give our speaker Kevin Wu another warm round of applause.